once again, this is non-Newtonian flows means a lot of things, or complex fluids means a lot of things. And there is not a single a single generic answer. There will be many different proposals depending on the type of non-Newtonian behavior you have. So I'm going to start with a very simple things, which was motivated by some reservoir engineering problem. So I will give more details in the case of a generalized Stokes equation. I will explain later what is it. But as I said before, there are many more potential applications for which you have to redevelop. Each time you have to look at the details of your particular thing. I'm going to go through rapidly the previous slides, which are the same as before. So I will essentially use some sort of upscaling techniques, which is used often in many applications, in particular reservoir engineering and digital rock physics. I will assume I have some sort of separation of scales. We have learned before that this is process dependent, and therefore, if I have another nonlinear problems, probably the notion of REV is not purely geometrical and would depend on the type of flow you are working with. So we already discussed that. I will also already introduce the fact that there are many upscaling techniques. Therefore, I'm not going to comment too much on that. Well, let me go back. I gave here the Dropbox link for those who want to download so I will put that later during the discussion so people can discuss that. I already give the fairy tale of upscaling for this simple example here. So the Paul scale thing, the representation in terms of some smooth average value and the deviation, and a coupled equation, and maybe a closure of the system, with a classical application in digital rock physics, which is some tomography reconstruction of the system, solving some local problem and calculating effective properties, which are useful in the macroscale equation. So that's the, as I said before, the fairy tale of upscaling. Now, let us start with something a little bit different than the Navier-Stokes equation. Now I have a non-Newtonian fluid with a rheology, a link between the shear rate and which is nonlinear, and which can be solved by solving which is called the generalized Stokes equation. So I have the Stokes equation in which the viscosity here is a nonlinear variable that depends on the shear rate. I will show later that there are other applications in which it's a little bit more complicated. So now here I have a nonlinear equation. I can, in terms of rheology, there are many different things. For instance, if I look at the viscosity with respect to the Newtonian viscosity, I often have a plateau at very low shear rates, a Newtonian plateau, and then something nonlinear. And I will use, because it's really illustrative, I will use this sort of plateau plus a power law. This is interesting, and I will explain later why. But there are many different possibilities. So we'll do the upscaling. Well, I will use a pedagogical picture, which is represented here. Like for the Navier-Stokes problem, I can work with the equation and show that the average velocity is almost constant locally in your reservoir, and locally also, so if you are far from boundaries, from wells, from whatever, and also that this average, the gradient of the average pressure is also constant. Therefore, what's going on here? If I solve for a problem in which I impose this as a constant, well, typically I will get something which is periodic here. Also the pressure deviation is periodic. We won't see that, but this is the orientation of the pressure gradient, and actually the orientation of the velocity orientation is a little bit different from this pressure gradient. I will comment on that later. And here you see the viscosity with tremendous changes of the viscosity. It drops rapidly in this constriction here, and it's a little bit different in the bulk of the pore scale. So now I have a nonlinear viscosity in the system. Let me say two things about nonlinear properties. I have two possibilities. Oops, there is no. Let us take, for instance, rho beta of the small scale pressure. Then I can write that of the average pressure plus d rho beta or dp. And it turns out that this is on the order of L over therefore, these terms can most of the time be discarded in the analysis. This is not the same for the viscosity that depends on the shear rate. Shear rate actually depends on V beta tilde or V beta. And it turns out that d beta, I already discussed that, is on the order of the average velocity. Therefore, you have two different mechanisms. If your density or the viscosity depends on pressure, and since pressure deviation is small over the system, you can locally assume it's constant. You will have to, as Jesus Carrère said this morning, you will have to take into account the large-scale variation of rho or of mu, but that's enough. Here, it's not the case, since it depends on through the rheology, it depends on V beta or V beta tilde. It's a zeroth order variation, so you have to take that into account, and that's very, very, very important. So remember, I have almost the same thing that before. I have those local constant. Therefore, I can work on the averaging of that. Let us skip that for the moment. This is in the PDF. Let us look at the equation written in terms of, let us tentatively assume that I have the same scaling that I introduced before for Darcy's law. Why this will not work? Well, it will not work because here I have if I have a constant viscosity, I have a linear relationship here, a linear relationship here. Everything is linear, and then I can solve in the framework of linear theory. But now it's nonlinear. Therefore, I cannot use that anymore. And therefore, the only thing I know is that I have a relationship between the gradient of the average pressure and the velocity. In the linear case, we already saw Darcy's law, so we have that. And in the nonlinear case, I will come back to that later, but in nonlinear case, what I have is the only thing I know is that I can write something nonlinear like that with an apparent permeability, which in some cases is called the permeance, but there is no, it's also used, this word is also used for something else, but this is the only thing I can write, theoretically speaking. It's not the way people want to represent things. So most of the time, they want to represent things in terms of what they already know for the medium, which is the intrinsic permeability. So most of the time, people will try to introduce, to relate that to the intrinsic permeability. The only general thing we can write is something like that. Like before for Navier-Stokes, I have here the Newtonian velocity, if you want. And the Newtonian velocity is corrected by two things. First, a rotation matrix, and then a nonlinear scalar that depends on the velocity of the system. And so I'm going to discuss what are the properties of those things. The way to do that is to analyze all those nonlinear behavior for different types of materials. So you can work with academic media if you want, or more complicated system. And I have to say a few things about one very, very peculiar problem, which is, well, I have so far essentially commented on the use of local periodic unit cells. But most of the time, we don't have a periodic system. So there are many things you can do. First, you may say, well, I want to stick to the periodic paradigm, and therefore I will make the image periodic. And there are many ways to do that. For instance, you can just translate the image, so it will essentially become periodic. But if you do that, you may come up with percolation problem, which is often the case. Or you can do, for instance, mirror image. But the mirror image essentially will change the anisotropy properties of the system. Or you may want to work in the framework of some sort of effective medium theory, which is essentially you add a small layer of an additional material, often 3 layer, and then you apply periodicity condition here. And so your result will depend on the thickness of this layer, but you may try to find if there is some sort of intrinsic value. But remember that if I don't have a periodic system, then I will have a result that is often biased by something. Another possibility, if you don't want to use periodic boundary conditions, is to use some sort of permeameter boundary condition. The most classical is the following. So I don't have a periodic system, and I just solve the local problem for a constant gradient of the average pressure over a system like that. Still, you can calculate some anisotropy, but you cannot prove the symmetry of the system. The symmetry of the permeability is proved from the closure problem with periodicity condition. If you remove the periodicity condition, you don't have the proof. Or you may want to relax the anisotropy. This actually forces a little bit the isotropy of the system. So you may want to relax that with boundary conditions which are a little bit more involved. So I still have a permeameter, but I accept to have a continuous variation of the boundary, the pressure at the boundary between the two boundaries here. So essentially, for those I'm going to present today, essentially for the media, like for instance X-ray tomographic images, I will use the thin layer method. So now let's go back to the system. So you have to solve for the problem. There will be a course on open form, so I'm going to skip that. But you have to be very careful because nonlinear rheology is quite demanding in terms of computational resources. And I will go through the results. Typical results will be the following. I will have the apparent permeability in one direction. Will depend. I will show a Newtonian regime for the particular rheology I was working on. There will be a transition. This transition actually will span over several order of magnitudes in terms, for instance, of a Reynolds number, if you want to define that. And then I will have some sort of power law regime. The velocity here is defined as the intrinsic velocity. So this is the typical observation I will do from this rheology. The structure of the velocity field is peculiar. See, this is the PDF of the normalized velocity. So the normalized velocity is the average velocity divided by, well, it's defined here. I guess, I hope. No. Normally, I should have put that somewhere. No. But the normalized velocity is actually divided by gamma, the shear rate times length scale. And with that normalized velocity, you can look at the differences in terms of topology, because if you don't do that, then there will be a difference, a huge difference between the PDFs. And the first interesting thing is that here I have a Newtonian results, and here I have the non-Newtonian results, and you see that all those PDFs are almost the same. All those normalized PDFs, this is really important, are almost the same. I don't know exactly how to explain that in details. I have some idea, but this is something probably very important that tells a lot about the kind of behavior. It looks like the things that determine the flow field for the Newtonian case actually involve the same geometrical features than the one that involves the non-Newtonian stuff. But this is an observation, but this is a statistical observation. It does not clearly show that if you look at the different flow fields. So this is a little bit more complicated to understand that. Transition, if you just look at the raw results, of course, there is a, depending on the material, it's like for the inertia term I discussed before. The transition spans over a huge, several order of magnitude in terms of the average velocity. But if you introduce this normalization, you have a more narrow cloud if you want, and that's an interesting feature. So you can look at the in terms of the representation of your own data, for instance, that can be interesting. But still there is some difference here. Please have a look at something here. Remember that my rheology was a plateau and a non-differentiable branching to a power law system. So it's not a continuous in the derivative. But here I have a smooth transition. I will use that later to comment on the implication in terms of engineering. But I don't have a sharp transition. I have here a smooth transition. Actually, there are a few poles that start to transition to non-linear behavior, and the statistics of that make a smooth transition, even if my rheology is not smooth. That's very important.
Can you remind us a little bit what the colors and symbols are?
Those are for the different materials I have introduced before.
All non-Newtonian? Or some of these are Newtonian?
The materials are A1, A2 are simple arrays. B is a Bentheimer sandstone, and this is another rock sandstone also, C1 and C2. So A, P, C, B are different materials, and which are represented here. This is different materials. Another feature which is important is the impact of the domain size, something which is often overlooked when people work with X-ray tomographic images. So to illustrate that, let us look at something which is an academic medium, which is made by the perturbation of a periodic array. So I have the periodic array here, and if I move all particles with a given variance, then I get something which is disordered. I will do the same thing. So I impose a certain macroscale pressure gradient with a given orientation. I calculate the Darcy velocity. So this gives me the Darcy permeability. And then I solve for the non-Newtonian case. So I calculate the average velocity for the non-Newtonian case. And most of the time, what I observe is that those Darcy velocity and non-Newtonian velocity are not collinear. This is particularly true for this system here. If I plot this angle, this is it is constant, whatever the size of the averaging, the representative unit cells you take, and it's not zero. It's close to minus 5 degrees. Now I do the same for the disordered medium, and I will do this, and I will look at two things: the impact of the variance and the impact of the size of the averaging volume. And what I observe is the following: if I have a small averaging volume, Then I have an average angle, which is non-zero, and the variance of that angle, which is quite large. And the good news is that if I increase the size of the averaging volume, then I get a much smaller variance and also a much smaller angle. This is the same for the nonlinear correction. Here I was looking at the rotation matrix, and now I'm looking here at the nonlinear correction. Nonlinear correction is constant for the periodic array, and the nonlinear correction goes like that for the disordered system. The value changes a little bit with the size, and then we get some sort of a plateau with a variance. And it's very difficult to decrease the variance because the non-Newtonian flow are really nonlinear. So a small change somewhere may have a tremendous impact, and therefore it's very difficult to have a. But we expect that if we had a much larger system, probably the variance will go down a little bit for statistical reasons. And that's very important for application in terms of digital rock physics, since most of the time people don't look too much about that, the size of the volume over which they calculate the effective properties. But if you take, for instance, the Bentheimer rock, and you do the same, I don't have a variance here because I have a single sample, but still I can change the size of the averaging volume if you want. And what I observe for an orientation which is not, which is 22 degrees with respect to the x-axis, I get something like that. So this is the size, this is the rotation angle, and after a while, actually, it goes pretty close to zero. So that's a very important thing. And if I look at the scalar coefficient that depends on the velocity, it does almost the same thing. So I go here, and I reach a plateau. The length scale here is scaled through some sort of equivalent radius, which is calculated through some geometrical feature of the system. But so you need you need to have more than 20 equivalent Power scale if you want to reach this plateau. So this is something, but this is something that depends on the size of the system. And now another perspective on that. This is the impact of disorder. I change the variance here from 0 to a highly disordered system. So I get a cloud of apparent permeability here versus the velocity. And in terms of the angle, I have something like that for for a system which is so the periodic array, disordered periodic array. I get something like that. I get a plateau after a while. That depends on the variance. And as before, for the Bentheimer rock, the B here, it does not change too much because I am already at something which is a little bit disordered. So, but you have to be very careful when using that because it's important to understand. So, what are the practical consequences? Most of people in engineering practice, they want to write the apparent Darcy's law, something like that. So they want to have the Darcy term corrected by the velocity rheology with an equivalent shear rate. Equivalent shear rate being defined by there are different formulas, but well, is it okay to do that? Well, we know that first, normally we have a rotation matrix times a Kn, the nonlinear stuff. So first, what can we say about the rotation matrix? If you are working with a disordered system and you have a size large enough, then we know that the rotation matrix goes to unity. So that's okay. For those disordered systems, that's okay to use K0 without a rotation matrix, first thing. Second thing is that, the use of gamma heck here is not correct in most cases. Remember that the plateau with power law has a sharp change in the derivative. And remember that our results show there is a smooth transition. So there is no hope to get that smooth transition by using the bulk rheology. Now, this is you may say that this plateau is not correct physically, but this is a good example. It shows that the rheology, just putting everything into the rheology is a little bit difficult. So you still, in most cases, you need the Kn. That's the point. That's very important issue. Well, let's skip the scale problems. Yes, I am almost done. Well, I'm not going to go into details, but first thing, complex fluids span over many different physics, and therefore what I have said has a limited application to the use of generalized Darcy's law, but the generalized Stokes equation. For instance, you may want to use viscoelastic fluids in which you still have your Navier-Stokes equation, or Stokes equation in most cases, but this time I have an additional term that comes from the more complicated rheology, which is, so this stress tensor here actually obeys a time-dependent equation that depends on rheology, which can be complicated. So don't look at the mathematics, but remember two things. This cannot be written under the form of a generalized Stokes equation with just a mu, nonlinear mu. You have a nonlinear mu, but that depends on an evolution equation. So there is a time-dependent potential effect, and the non-linearity may be complicated. And it turns out that many fluids behave like that. So you have to be very careful when talking about nonlinear physics. You have to understand that. And last example, if I take one example of rheology, I still can write the equation under the form of an apparent permeability, but the apparent permeability will depend on the velocity, if you want, for the Deborah number in a highly complicated manner that depends on the rheology of the system. And this is for steady-state situation, but for those familiar with viscoelastic fluids, we know that there might be also some elastic turbulence in the system, which could be important for highly permeable media. And last thing is, well, if you apply that to a polymer solution is not a single chemical species. Actually, you have several chemical species. They have the same formula, but the chain is different. So therefore, this is a multi-component system. And so therefore, there is a need to approach that also from a multi-component point of view. And there are questions about how to write the momentum balance for such a system. Generally, the PDF or your prepared solution is something like that. And when your solution goes through a porous medium, then we get something different with eventually several bumps depending on the structure of the system. And so this is still an open problem, and it cannot be solved like I have proposed only through an apparent permeability. You have to solve for the composition, quote, of the polymer solution. This is quite an open problem. But we have observation. There is experimental evidence on that in many, for instance, many petroleum companies. So that ends my presentation. So remember, I have here, still I can write, at least for the generalized Stokes equation, an apparent permeability. The apparent permeability may show an anisotropy effect due to non-linearity. And there is a correction that does not always fit with the traditional engineering practice. And that, well, there are many open problems, and we are still trying to understand much more complicated problem. Yves is going to talk about foam, which is another example of a quite complicated material. Asking a question about, what is your specific question? This is a form of Cauchy equation for a two-component fluid.
So the second part?
So, well, that's an interesting question. So, you can write it, you can forget about the solvent. But for most of the time, for those viscoelastic systems, it's applied to some polymer or things like that. So the idea is I have a solvent, And I have particles that can stretch, can change the shape during the flow. And therefore, I will write the equation like that with a Newtonian contribution and a non-Newtonian contribution. And since it can stretch, it's a mixture of springs and things like that. So the behavior of that non-Newtonian part, viscoelastic part, actually is quite complicated and depends on an evolution equation in which I introduce quite complicated behavior that depends on the structure of your molecules and things like that.
So it's the dynamics of the microstructure, basically.
Yes, yes. Yes, typically, well, there are many, in the literature you will have a lot of results for all rod B, but all rod B is a spring, but that can extend infinitely, and therefore, at some point we solve the problems about there is no limitation. So Phi P is the all rod B, if you want, with a limitation. At some point you cannot stretch the molecule anymore, which is, and there are other type of rheology. As I said before, there is a huge class of families and each having particular properties. So that's why I don't have a generic proposal for non-Newtonian flows. And you have to just illustrate that.
At the risk of doing violence to a lovely mathematical presentation, you seem to have shown some elegant similarity between Newtonian and non-Newtonian fluids that was quite surprising at some level.
Yeah, yeah.
That, I think, hints at a very important simplification. And that is, when we have a power law change in viscosity, effectively it breaks into two regimes. You have either Newtonian flow, or in the non-Newtonian case, the flow regime breaks into that region which has high shear, which becomes fluid, and that which is low shear, which is essentially inert. Mm-hmm. And so we essentially then could look at this almost like a green and amp sort of world, where we simply break it into two effective fluids. We calculate the mean shear in the moving fluid, get an effective viscosity there, calculate, and then essentially consider everything else inert. I think that perhaps we have to back up a little bit from the mathematical form and look more at the structure of the flow and what it means to have a power law viscosity.
Yeah. Well, of course we look at all that. But it would take time to that's why if I look at those PDF, for instance, the reason for which they are similar between the Newtonian stuff and the non-Newtonian, at first we thought that it's just the amplitude of the shear rate that changes, and therefore it's almost just a scaling through the velocity of the system. It's not exactly that. They are so the pore constrictions that determine the Darcy permeability are not exactly the same that the one that determines the non-Newtonian Darcy permeability. So that's this result is more due to the statistical the ensemble averaging, which is and first thing.
Very important.
This is very important. This is very important. This is very important. But remember, this is a PDF. If I look at the fields, I will see differences in the place where the pressure drop actually arise. That's very, very important. Remember, this is for this particular case of non-Newtonian rheology. For viscoelastic system, it's a little bit more different, and we are not sure that this is we have something similar.
We go to the next plot, and then where you have the hockey stick, we call it. Okay. Now, if you were to calculate on the right-hand plot the apparent viscosity given the mean shear rate, that power law behavior says, oh, that's exactly following the power law viscosity. So if we were to correct for the rate of shear, that would be a straight line.
Yes, but well, so the discussion here is a little bit more important. If I don't take into account any wall effects, like exclusion zones like that, I have the same. I can calculate directly this the power here from the power law n. But if I add additional physics, then it's not the same. That's the first thing. And second, here, remember that we have a transition here that does not fit with the use of a bulk rheology for describing the transition. This is one order of magnitude.
But the first order effect should be accounted for.
Well, but if you are near a well, for instance, you go from that through that, and therefore you may make some error. But I'm just pointing that because it's not in the reservoir classical models. There is no most of the time because of this bulk rheology, you will have here a sharp transition, which is not correct. And since this is it's one order of magnitude between it spans over more than one order of magnitude.
But vertically, it's not one order of magnitude in the vertical.
Yes.
The error is
yes. Well, it's factor 2, depending on the type.
Like
yeah. I'm just pointing at that. So the engineer knows what he's doing. It's the same for the rotation matrix. I mean, the rotation matrix, probably if you take a very large sample, will be unity. If you are not careful enough, for instance, using your X-ray tomographic image, you may actually compute something which is in a range of value for which P is not equal to unity. So you have to understand what you are doing. But the reservoir engineer they will not use that if it would not work most of the time. So they have a lot of experience.
I have a question related to your picking the right scale.
Yes.
I mean, you need to have this separation of scales, obviously, and you've got to have, if it's random, you've got to have a sufficiently large sample. And then you might run into the problem that this sufficiently large sample is then so big that you have other trends. Let's say you have, if this is a sandstone, that you have a fining up or something like this. And so what are you doing if you have evolving scales?
Well, let me say something. So I said, well, I must have a separation of scale. So that's the mathematical requirement. But in practice, I've never that. And that's the interesting thing. So in many cases, and for instance, in reservoir engineering, we never apply the technique in such a case because we have evolving heterogeneities. So let me take an example. And I will draw sort of a recommendation. Let's take fracture system near the percolation threshold. I can solve with that, or I can just say, well, I'm going to do that. I'm going to, stupidly, I'm going to calculate the permeability. So I will have a permeability, you see, very small, here probably like that. I don't know, like that here, like that here. I'm drawing the axis, the principal axis and the value. And it turns out that I can calculate some effective permeability solving the exact percolation problem. Or I can calculate the effective permeability through some sequential upscaling. And I have two things. Actually, they are very close, not exactly the same. For instance, you know that near a percolation threshold, you have some sort of power law expression of the effective transmissivity, which I will not recover with this kind of stuff. But it works relatively well. And this is used on a daily basis in reservoir engineering. In reservoir engineering, people, they take their reservoir and they put heterogeneities everywhere. They don't care too much about the contrast between permeability, which is a problem because, as you mentioned, I have evolving heterogeneities. Therefore, I'm not in the pure framework of any upscaling theory, whatever the theory. But it works relatively well. It's very difficult to predict the error you make, and that's moral because you are far from a nice mathematical theory. But it works. It works, and therefore the recommendation is that Well, if you have a multi-scale system, especially with natural system, well, do actually a sequential description first, and keep as much as you can large-scale heterogeneities in your final system. Why is that? Because we know when we have evolving heterogeneities, we have to take care of those non-homogenizable situation, and therefore it will be better taken into account if you keep in your final description most of the multi-scale feature of the system. But down to that, you can use approximately that.